Okay, for 10.5, let's look at number 3. How productive are U.S. workers? One way to answer this question is to study annual profits per employee. A random sample of companies in computers, which is the first category, aerospace, number 2, heavy equipment, number 3, and broadcasting, number 4, gave the following data regarding annual profits per employee. And these are in thousands of dollars. So the question says, shall we reject or not reject the claim that there is no difference in population mean annual profits per employee in each of the 4 types of companies? So this is kind of worded a little differently than what we had seen before. It's really saying, should we reject or not reject the claim? They're claiming there's no difference, so they're claiming the null, which is a little bit different. We're still finding enough statistical evidence to prove the alternative. So if we don't have enough statistical evidence to prove the alternative that they're different, we have to assume that there's no difference. So it's just a little tricky in the wording there. Okay, so the way we're going to start this problem is we are going to put our data in our calculator. So if you watched the lecture videos, he talks about now what happens is we're dealing with more than 2 groups, right? So in 8.5 we had 2 populations. Now we have 1, 2, 3, 4 populations, or 4 different groups. So our null hypothesis is that we're going to assume that all 4 of those means, population means, or the population mean annual profit per employee in each of those groups is equal. So since we have 4, we're going to have 4 mu's being equal. So this is a little tricky on the alternative. You don't want to say that they're all different. So what you're testing is at least 2 of the means are not equal, or not all the means are equal. Meaning if this one is different, then they're not all equal. These 3 could be equal, but this one would be different, okay? So that's why you don't want to put a not equal to in between these, because you're not testing that they're all different, just they're not all equal. So at least one of them is different, or at least 2 of the means are not equal, okay? They could all be equal. So these are 2 different ways we could say the alternative there. Okay, so when we do our ANOVA test, this is called analysis of variance, or shortly we say ANOVA, okay? And the test statistic we use is called an F-test statistic, okay? So when we get to step 3 and do the critical value, the F distribution, and if you hopefully watch the lecture videos or read through the section, it tells you a little bit about that distribution. The 2 distributions we used so far are the normal distribution, standard normal distribution, which was the z-table, and the student t-distribution, which was the t-table. Both of those were symmetrical. The t-distribution had fatter tails. As the sample size increased, it got closer and closer to the normal distribution. The F distribution is not symmetrical. It is right skewed, okay? So when you draw your picture, the F critical region or rejection region, we're going to find an F critical region here, it is always right-tailed. Okay, so in these problems, the null and alternative are always going to look like this, although you'll have, depending on, you could have 3 groups, 4 groups, 5 groups, however many groups you have in the null. And then the critical region is always going to be right-tailed. Okay, so when we do, in the way we find the F test statistic, we create what's called an ANOVA table, and this says analysis of variance. So ANOVA tables are going to have these different values in it, and they're used to compute the F-test statistic and the p-value. Obviously, these are the 2 things we're going to look at to make our decision, but this other information is used to compute that. And they're all about, this is called this is degrees of freedom, this is sum of squares, and this is mean squared. So sum of squares are just calculating a lot of sums. So what the calculator will do for us will give these values that we would fill into this table. If we were using a computer program such as SPSS, Minitab, Excel, it would give you the whole table and you would just look at these 2 values. So if you look in your textbook or even online, you will find some ANOVA tables that it'll show you that computer programs do spit out. Okay, so I know in WebAssign it asks you for some of these values, so I want to show you how the calculator gives you those. All right, so in this example, let's go ahead and go Stat, Edit, and put in our 4 lists. I'm going to put the first one in L1, the second one in L2, third one in L3, and then the fourth one in L4. So go ahead and do that. Now, once you have the data in, we're going to create our ANOVA table. So we're going to go Stat, over to Test, just like we have done before. You can either scroll up or down. I kind of go up because it's the last one that says ANOVA. Okay, now your other calculators, you have to put in which list. So I'm going to tell L1, comma, L2, comma, L3, comma, and L4. Got it? Hit enter. And it's actually going to start with your F-test statistic and p-value are the first two things the calculator gives you. So I'm going to write those here. I'm going to just round this to 2 places, 0.85. P-value, remember, always round to 4 places, 0.4867. See that? Okay, now, if you notice this says factor, so basically in the ANOVA table, these sums of squares, this is between or factor. It means what's the variance between the groups. And the second line says within, and on our calculator it will use the word error. And that just means the variability within each group. So these are the variability between the factors. Okay, so the degrees of freedom there is 3. On my calculator, see how it says factor, degrees of freedom. And then my sum of squares is 89.63. I'll just do 3 decimal places, 7. And my mean squared is 29.879. And see this arrow? This just means you can keep arrowing down, and you'll see the word error. Keep going all the way down. Gives you degrees of freedom, sum of squares, and mean squared. So our degrees of freedom there is 18. Sum of squares, 635.83. We'll do 827. Sorry, we were doing 3 decimal places. Mean squared is 35.324. Okay, now to get our totals, we just add these. 21, we add these two together. That'll give us a sum of squares total, mean squared total. So basically when you do this, just for your information, once you have the ANOVA table, if you take the sum of squared divided by the degrees of freedom, it will give you the mean squared. Sum of squared here divided by degrees of freedom will give us our mean squared. We divide these two, 29.879 divided by 3.35, and it will give us our 0.85. I mean, that's just how the table works. Once you have these first columns, you just divide to get these other ones. Okay? So that will allow you to put the information into WebAssign. Sum of squares between is right here. Mean squared between is here. Sum of squares within, or it's going to show up as error on your calculator. Mean squared within, and then totals, just add them together. Okay, so to finish our test, our F-test statistic was 0.85. We do need to look up our table. In order to do that, we need the degrees of freedom for our numerator and the degrees of freedom for our denominator. So remember here I said you're going to take the mean squared between divided by the mean squared within. So it's degrees of freedom numerator, degrees of freedom denominator. So my degrees of freedom numerator is 3. So we do need those to look up our table values. So the F table is in the back of your textbook. I will print these off for you as well for your tests. But it begins in Appendix 2. It's Table 8. I'm going to pull this up here, and the picture shows it right-tailed. So what we need to do, across the top is degrees of freedom numerator. Down the side is degrees of freedom denominator. So since our degrees of freedom is 3 for the numerator, we first have to find this degrees of denominator and what page it's on. Since ours was 18, we have to turn the pages here a little bit. And we'll see 18 for the degrees of freedom denominator. Our degrees of freedom numerator is 3. So we're looking in this group right here. Okay, do you guys see that? Degrees of freedom denominator is 18. Degrees of freedom numerator is 3. And then what we do is look at our alpha, or our level of significance. In this problem it was, I forgot to write it down, didn't I? Sorry about that. Let's go look it up real fast. That's why you're supposed to write it in step 1. I think it has you do it. Alpha's 0.05. Level of significance. Okay, so our degrees of freedom for denominator is 18. Numerator is 3. Alpha 0.05. So in this little group right here beside the 18, this brown area, I look for 0.05. Go over to 3. 3.16. Okay. So looking at our test statistic, 0.85, is that to the right on a number line or left of 3.16? Clearly it's not more than that. It's to the left somewhere. Okay, so that does not fall in my rejection region, correct? So we're going to say do not reject H naught. Don't forget to put H naught on there. Some of you have forgotten that. Okay? Our p-value statement, we're going to reject H naught if the p-value is less than alpha. So we want to see if, did we write down our p-value? I actually didn't, did I? P-value is 0.4867. I think I wrote it in the table. 0.4867. Is that less than 0.05? No, right? So we do not reject, or on the WebAssign, do not reject H naught, we would say fail to reject H naught. So those two are the same. They have to be the same. Okay? So our conclusion then is at the 5% level of significance. We can say this the same way. As we had done before, just have to be a little careful that you don't go back exactly like the problem is saying, because they were talking about the null. Okay? We do not, just like before, since we did not reject, we do not have enough statistical evidence to conclude that all, okay, well, we want to say that the alternative, that all the means are equal. I'm sorry, not all the means are equal. So to conclude that at least 2 of the population mean annual earnings are not equal. Okay, so I think on a WebAssign it would say there's insufficient instead of saying not enough statistical evidence. Insufficient evidence to conclude that the means are not all equal. Okay, we don't have enough evidence to conclude that one's different. Therefore, we have to assume that they're equal. So we would not reject the claim that they're the same. Make sense?